So the next speaker is Hirsch Kauffman from University of Chicago, and he will speak about everything we already know, the basics of Khovanov homology.
So this is meant to be an elementary talk about Khovanov homology, I claim it rearranges some of the things that everyone knows. And another part of the theme is well illustrated by this this nice drawing by Escher. The little dragon is doing his best to try to get out of the plane. He has some troubles. So I begin by reminding you about bracket polynomial. Let's see, does this work? Yeah. So bracket polynomial model of the Jones polynomial, but it's been reconfigured for our purposes with instead of something like A and A inverse here, I have a minus Q multiplying the second one, and the value of the loop is Q plus Q inverse. This is just a reconfiguration of the usual bracket, but it means that when you normalize it to get something that's invariant, to get the Jones polynomial, you have to do a slightly different counting. And I don't know if I'm going to use this, but I'll say it carefully now. I take the n plus to be the number of positive crossings, and n minus to be the number of negative crossings, and then you use this expression here, and you will have the Jones polynomial back. It's an advantage if you're thinking about the loops, to have them evaluated by something a little bit simpler than usual. And in fact, we're going to do another thing, an idea due to Vero, which occurred after Khovanov invented the Khovanov homology, and that is to think of the bracket expansion after you've enhanced the states in the state summation, the states being all of the loops configurations that you get by smoothing the crossings, of course. Well, then I'm going to have positive loops and negative loops. And the positive loops will be evaluated to Q, and the negative loops will be evaluated to Q inverse. And then that means that when you finally get down to evaluating some configuration of loops, it'll have plus or minus signs on it, and there will be sites here which either received a 1 or received a minus Q, depending on which way they were smoothed. And so the individual state, a bunch of loops with no crossings, will contribute a negative sign raised to the number of minuses that occur there in the sites, and a Q, which is raised to some power, which is coming from the number of smoothings that happen this way, and the number of plus minus the number of minus loops that there are. So you get one monomial for each state, and that's convenient for thinking about various things about the bracket expansion. And if one had decided to think about the bracket like that from the beginning, then one might have rewritten into the next line, which says that we could take the sum over the dimensions of the module generated by those states which have a particular I and a particular J, so they would be giving the same contribution. So I'll just call it a dimension, and then I have a module which is generated by those particular states. And we'll see that that is leading us to the homology. Oops. So I illustrated, just for if you hadn't thought about it before, what's going on here by labeling things with pluses and minuses. You see, if I do that and then I had two loops next to one another and I think of multiplying them formally, then I have all of these different states that could occur, right? Plus and all minus. And each one gives rise to a value, Q squared, 1, 1, and Q to the minus 2. And you see that that's exactly the same as raising Q plus Q inverse to the second power. So that in the usual expansion of this kind of situation where you have some number of loops and you take Q plus Q inverse to that power, you'd be applying the binomial theorem to get some evaluation in the polynomial. But here it's happening automatically because the binomial theorem has been released into the combinatorics of enumerating all of these state loops that are labeled plus and minus. And so that's why you don't see any binomial with a power in here, and why it's easy to go over to that. Of course, we're thinking about some knot and its various states. And if it were the trefoil knot, then there would be 2 smoothings for each crossing, and you would end up in this pattern of all 8 of the states of the trefoil knot. Now I've labeled them A and B according to the usual convention. That this is an A and that's a B, so that one can keep track of bookkeeping, but they aren't the variables anymore. So, so you have a cube, as Khovanov taught us to think about these states in terms of a cube. And of course you have a cube because you have for each site you have two choices, A or B, and so you will form a 3-dimensional cube if you have 3 sites, and you will form an n-dimensional cube if you have n sites. And furthermore, it's amusing to think of the structure of that cube as coming from adding an extra arrow to the algebra of raising something to the 3rd power. You see I have A arrow B cubed. Let me illustrate on the next slide what I mean by the element. Whoops, that's the wrong next slide. Thought I had a next slide. It'll come later. Let's continue the discussion as I have it now. In any case, you have this cube of states, and if we're thinking about the new states that I just described to you, then you have a lot more, right? Because this gets a plus or a minus, and this gets a plus or a minus, this gets a plus or a minus. So there are lots more depending on how many loops there are. And so each one of these has a lot of states in behind it, having to do with the pluses and the minuses that we put on it. And now getting back to what I was saying before, I'm using the enhanced states, and I have written the polynomial this way, and I can rewrite it as the sum over all state of the dimension of all states which have a given pattern I and J, all states which have the same contribution. And then if you continued formally with that, you could rewrite it as the sum over the j's of the sum over the i's, and you had a -1 to the I dimension of Cij. So staring you in the face there is an Euler characteristic of a something. But of course, at this stage, I haven't told you any boundary mapping, right? So this is what Khovanov found, if you want to look at it this way, that there is a boundary mapping from the module Cij to the module Ci plus 1j. And the j remains fixed under the boundary mapping, and boundary squared is equal to 0. And so it happens, and we'll go into the story of that in more than one way, but it then happens that you can write the Jones polynomial as the sum of powers of q times Euler characteristics of these homologies. And there's more than one homology. There's one homology for each j, as you see. And each one has its own Euler characteristic, and it will turn out that each one is an invariant of the knot in an appropriate sense. So when you speak of Khovanov homology, you're speaking of a graded homology, and that's the grading in the situation. Now, where does this come from, this mapping from on the boundary? In order for the j to, so let's just play with numbers for a moment. In order for the j to remain fixed, that means that I need that the lambda, which is the number of positive loops minus the number of negative loops, should go down by 1. The reason it has to go down by 1 is that the j counts up 1 more if there's 1 more b smoothing. Remember, we have the smoothings, and if there's 1 more b smoothing, then you pick up 1 more q. And that's what happens when you are going from here to here. And I guess I'm trying to say things in the simplest possible order, so everything is coming from the ordering in that cube, which tells you that you're going this way, like that. And that's going to be the boundary. That's going to be a piece of the boundary. That when you change a state from an A smoothing to a B smoothing, that's going to be what happens when you apply the boundary map. You're going to do that one site at a time across all of the different possible ways of doing it. And so when you do that, the j will go up by 1, but the j would go up by 1 if the lambda didn't go down by 1. So if we want to do a little counting, we can do this by asking what would it be like for the number of plus loops minus the number of minus loops to drop by 1 under those circumstances. So I want to repeat myself, if you don't mind, and go back to the cube again. What you have here, and what tells you what kind of boundary map we're going to construct, is you have a little category which has objects which are these collections of loops, and arrows, which generating arrows, which are taking you from one state to the next state by resmoothing at exactly one place an A to a B. That's how the cube is generated. So if you think of the first state as having just 3 A's, then there are 3 lines out to changing one A to a B. And if it has a B and an A and an A, then you can change it again and so on. And you go down through the cube that way, orienting it. And this little category, if you were thinking abstractly enough, and maybe this was the way he was thinking originally, Khovanov, I don't know, you might say, well, what would happen if I took the cohomology of the nerve of that category? And that's really the idea behind the Khovanov homology at a certain level, that you're looking at the cohomology of the nerve of that category. But if you looked at the cohomology of the nerve, and I'll come back to this later, I'm not going to do it this way, you would be looking at series of compositions of arrows in the category. So you would have, for example, this arrow, this sequence of arrows going down through the category, and then you might say that its ith boundary would be obtained by composing 2 of them and getting a shorter sequence and playing like that. But what presents itself when you're looking at a category as simple as a cube like this is that it looks very much like the usual kind of boundary maps in algebraic topology. That from a given point, you have a number of partial boundaries, partial directions that take you out into something which you'll regard as the next stage in the chain complex. So what one is going to do is one is going to define partial boundary mappings corresponding to each one of these arrows, and then take the sum over those partial boundary mappings from each point. And then vertically, the next level in the chain complex is going to be the direct sum of these modules, then the direct sum of these, and that. So that's the way the boundaries are going to come about. The boundaries are coming about from this arrow replacing the usual sum over A and B. It's that arrow that allows things to happen. If there weren't some ordering of this kind, then we wouldn't be able to get started at all. So now we're in a position to do a little exercise. And the exercise is the following. Here are 2 circles, and I want to figure out what to do with them under the partial boundary mapping. Now the partial boundary mapping is going to apply to these 2, and it's going to give me a new one, or sum of ones, and I want the lambda to go down. Now what's lambda? Lambda is the sum of the pluses minus the minuses, so lambda is 2 here. And when you go over here, re-smoothing it, you have a single curve, and you would like to label it. And if you labeled it plus, then the lambda goes down by 1 and you're good. If you labeled it minus, you'd be in trouble. So it has to be labeled plus. If you have a plus and a minus, then lambda is 0. And when you re-smooth, you see putting in a minus takes it down by 1. Putting in a plus wouldn't work. And if you have 2 minuses, well, that's minus 2. And I can't take it, and I would like to take it to a single circle, but I can't label it and make it go down any further, so it goes to 0. If you let x denote the minus and 1 denote the plus, then you see an algebra structure. The plus is acting like an identity, and of course this is plus or minus or plus. It'll go to minus either way. The minus, the plus acts like an identity. The minus seems to have square 0, and so we have a bit of algebra here with square 0, x, and 1 is the identity. And then you can say that when you have 2 circles and they're labeled in this algebra, then if you just multiply in that algebra, then you will get the resulting correct labeling in the module that corresponds to the circle on the right. So now I'm speaking in a language of modules associated with circles, and of course that's the next step in thinking about it. Each circle is going to be a module. The module is going to be generated by the pluses and minuses, or the x's and the ones, however you like to think about it. Each circle is, all by itself, the module z of x modulo x squared. And we have a product if two circles smooth to a single circle. On the other hand, a single circle could smooth to two, and you can ask what will happen there. So if a single circle looks like this, and it's labeled x, which means the -1, and it goes to two circles, and we want the lambda to go down by 1, then we can do it with no trouble at all by labeling one x and the other one x. And that suggests that you have a coproduct going from the module to the module tensor the module, two circles. Delta of x should be x tensor x. But on the other hand, if it's labeled 1, that's lambda equals 1, and it's supposed to go down to 0. Now 1 plus -1 is 0, but -1 plus 1 is 0, and there's no reason to prejudice one over the other. And so that suggests that delta of 1 should be 1 tensor x plus x tensor 1. Giving you the coproduct mapping from V to V tensor V. So just the condition that the J remains fixed fixes you into this algebra that describes how the boundaries will go. So now we're at the following stage. This is the way it might have been guessed at this stage. That you have a module associated to each state circle. There should be, because of the smoothings, multiplication and co-multiplication maps on the module, and those co-multiplication and multiplication maps are this simple if we just ask that J remain fixed. And then we'll have a boundary mapping. Do we get something which has boundary squared equals 0? Now, I forgot whether I put it in the slide immediately or not. I've arrived at an algebra, that's a Frobenius algebra, and there's more work to be done. And I have a feeling I want to go to the blackboard here. Yes, okay. So what I left out of the slides at that point, let's go back. What I left out of the slides at this point was, how do you know at this stage that you have a chain complex? Let's just stop at that point. How do I know I have a chain complex if I do this? I have a mapping, but is the boundary square going to be equal to 0? So I'm looking for an eraser. Yeah. So let's worry about that for a moment before going on. So what I need is the following: that if I start somewhere and I do one of these partial boundaries and end up somewhere else, and then I do another one and I end up somewhere else, that I might have done it in the other order. And mod 2, I want this to be the same. Because when you take a boundary twice, that will mean that every term in the boundary will occur twice. Once in the form of the I thing and then the J thing, and then around the other way, the J thing and then the I thing. So this will imply that boundary squared is equal to 0, mod 2, and then if you put the signs in correctly, everything will work over the integers, and I won't worry about anything but mod 2 in talking about this. So this is what you need. Now let's see what it means in terms of this geometry of circles. Suppose we take these two, and suppose that I think of, oh, excuse me, one more thing. When I take a partial boundary, it can be thought of as a little surface cobordism, like that. Because we're smoothing, and it could go the other way if it's the other way. So suppose you take this one, and you think of doing this one first and this one second. So then you will be forming a coproduct here and carrying this one along. and then you will be multiplying this one and carrying the other one along. And that's what would happen if I did first boundary 1 and then boundary 2. Now on the other hand, if I did 2 first, I would multiply, and then 1 is still available to co-multiply, and we would have gotten this situation. So this is boundary 2 applied first, and then boundary 1. And then what you want to see is that the algebra is so good as to actually give you the same results for both of these situations. And so one exercise will suffice, right? So suppose I do 1 and x. Then 1 times x is x, and this is x tensor x, and that's what comes out the other end. On the other hand, if I have 1 here and I have x here, then at this stage I have 1 tensor x plus x tensor 1, and over here we have x. And then what this means altogether is 1 tensor x plus x tensor 1 tensor x. And I'm going to operate by multiplying in the second factor. So I multiply x times x, and I get 0. And I multiply 1 times x, and I get x. And so this gives me x tensor x. So down here, that's all that's left. The 1 tensor x goes away, and the other one survives. And you can check that by some miracle, this algebra actually works just fine and gives you all the compatibilities that you would want, and that it's producing a small topological quantum field theory for circles and surfaces in that what the identities that are working here are exactly that the intermediate surfaces are homeomorphic. Whenever they're homeomorphic, you will get the same map. And of course, you can write down some algebra axioms for that, and when you've finished writing them down, you'll have the axioms for a Frobenius algebra. So far so good. We really have a chain complex. But what you can't see so easily at this stage is that this is going to give you an invariant of knots. So this might be lesson number 1 in Khovanov homology at a certain stage. That is, you can see how cleverly you can build a chain complex and that it has the right properties and that it's related to some cobordism geometry. But why is this managing to be invariant under Wednedsay moves? That is not obvious at this point. So I want to go farther and work on that. And in order to work on that, I'm going to be less algebraic, not more algebraic, because I'm rearranging things a bit. I did want to mention one last thing. You might wonder, well, in what way does the thing end up being invariant under Wednedsay moves? And the answer is back in the knot polynomial for this version of things, because we know how the knot polynomial behaves under Wednedsay moves. And you have to rewrite it a little bit if you're using the Q that I'm using. You see, when you do a 1 move, it shifts it by Q or Q inverse. And when you do a 2 move, you can also pick up a shift. And when you do a 3 move, you don't pick up a shift. And you'll sometimes forget to draw a line. So these grading shifts mean that the homology will shift along correspondingly, and you won't have that the ith homology group of one is the ith homology group of the other. You'll have to shift by the corresponding grading. We'll see that when we look at an example. So here I am with the cubism again and this side remark. The side remark that I wanted to make was about elementary algebra, and also about wondering how to do this more generally. Now the elementary algebra remark is, let's suppose that you decided to square A arrow B. And you decided that you would have the distributive law for things like this. Arrows arrows could distribute across elements just as though you were multiplying in the usual way. And then elements can distribute across arrows of elements as well. So two distributive laws interacting. And you see that it expands out into this, which looks like an arrow between two arrows. We've arrived, by generalizing elementary algebra to algebra with arrows, we have arrived at higher categories at once. So this is my pitch for teaching higher categories in the 9th grade of high school. Not really. But you see, then I want this arrow between two arrows to be collapsed to arrows between objects in this way, and we land on the cube category. So in that sense, A arrow B to the nth power is a higher category with a lot of tiers in it, and you collapse it and you get the cube. So the category comes out of composing or multiplying single arrows. Now the reason I mention this is because I'm thinking about how it looks from the point of view of quantum topology. And in quantum topology, you think of a Morse diagram for the knot. And then it would be natural to think of this bit of braiding as the square of the arrow that is associated to a crossing. Instead of an R matrix associated to a crossing, an arrow is associated to a crossing. Instead of a composition of those R matrices in the category, you have a composition of powers and other things in the category. And you see that what's going to happen is that if you expand in this way, you get a category out of the Morse diagram. And then that category has some kind of homology associated with it, and there comes the Khovanov homology. So the question is there a way to configure that for a more general quantum topological situation where you have an R matrix? And of course, some answers come from work of many people like Ben Webster and Anna Belyakova and other people, and Catherine Struppel, who use a lot of representation theory and come to something like this in the sense that each of the individual bits of the quantum topology, the cups, the caps, the crossings, turn into functors, and the things work out. But one would still like something as simple as the way the Khovanov homology works. So I'm just pointing out that from this Morse diagram or quantum topological point of view, the Khovanov homology worked remarkably beautifully, expanding the knot diagram into a category in a way that generalizes the way you used to think about putting R matrices in. And so this question hangs over it, whether there would be an elegant way to do this for an arbitrary link invariant made out of R matrices and cups and caps, but no one knows. Let's see now where we are. I already said this about the maps and the surface cobordisms, and how the complex looks from this point of view. And there's the diagram that I drew on the board. I forgot that I had a slide for it, but you don't mind. Now I'm going to go up a level using an idea that, beautiful idea of Dror. Dror's idea is the following. He calls it the canopoly. Instead of the chain complex, you have the canopoly. And the canopoly is the following, that you have this category, and you've decided from the algebraic point of view that you're taking the direct sum of the vertical stuff to get the chain complex elements. So you get a chain complex out of the category by taking the direct sum of those vertical pieces in the states. Well, why not take the category and just take the formal direct sum of those things and associate no algebra to them? So you've just packed the category up into something that looks like a chain complex. You have all the partial mappings, but the partial mappings now are generated by elementary cobordisms of circles to other circles. So you have cobordisms like these, and you don't have any algebra. No algebra stands. You only have possible compositions of cobordisms. Compositions of cobordisms taken up to homeomorphism will satisfy all the compatibility conditions, and so you will have that the boundary squared will be equal to 0 in the sense of repetition. And you have an abstract chain complex with no algebra in it. No kernels, no co-kernels are available to you, but you do have something which looks like a chain complex and is subject to discussion such as, is this one chain homotopic to that one? Is a certain map homotopic, chain homotopic to another? Because chain homotopy just means that there is a certain mapping going up the grading that satisfies a certain relation. So that's the canopoly. The canopoly is the bare bones of the chain complex without any algebra put in. The mappings are now just bits of cobordism like that. That's all you have. And of course, as I said, I'm going to work modulo 2. And I want to think about this. Now, if you read Dror's paper, maybe a little too early, he tells you the answer to this question. The question is, what is the least equivalence relation on the canopoly such that the canopoly is invariant under the Reidemeister moves? All right? So you see, you have this thing which looks like a chain complex, and you have the notion of chain homotopy, because chain homotopy is just having some mappings like that, and you don't have to take any kernels or co-kernels. It's just a certain kind of structural relation. What's the least equivalence relation you would need in order to get things to be invariant under the Reidemeister moves? So let's examine the second Reidemeister move and think about what those complexes look like. Now, you don't have to think entirely abstractly. You can just say, I'm taking pictures of a cobordism type of a possible chain complex, or you can think entirely abstractly that I'm working in categories where the mappings are just these cobordisms. However you want to think about it, these are the pictures. Here's the picture of what happens locally when you expand on a Reidemeister 2 move. And so you see that if you didn't have the Reidemeister 2 move, you would have nothing at all. And so I've written empty, but of course this means that there's the rest of the complex is sticking in there. It's just unknown to us. And I'm placing this one in comparison with the middle part of that one. And if you were to check my grading instructions from the other slides, you'd see that's the right place to place it. But it is intuitively the right place to place it. What I want to see is that these two structures are chain homotopy equivalent to one another. So I need to get mappings back and forth between them, and I need to make chain homotopies as well. And let's think about chain homotopies for a moment. Well, no, let's think about mappings for a moment. Suppose I want to map this one into this one. Well, I can map it into the upper one by just taking it identically, and I can map it into the lower one by giving birth to a circle. That's a cobordism. What about mapping this the other way? Well, I can map this one identically, and I can map this one to that one by letting this circle die. So I have mappings F1 and F2. There is, oh, I see, I drew it horizontally over here because I thought it was easier to do the labeling horizontally. So maybe you want to look at the horizontally labeled one because that corresponds to the maps. It's just exactly the same, all right? So I have F, which goes upward, and F gives birth to a circle in one case, and F just is the identity in the other case. And I have G, which goes down, and G is identical here, and G lets a circle die here. And what about the mappings? The boundary mappings are little cobordisms of the types that we've indicated. And then there's the matter of chain homotopy. Now, if I want to show that a composition that takes me from this one back to this one is chain homotopic to the identity, I'm going to need a chain homotopy, which is going to go backwards in the complex direction. And this is the chain homotopy that suggests itself. Let this circle die, and you'll end up here. Give birth to a circle, and you'll end up there. All right? And then you need to do some checking to see whether your conjecture about all of this works. You need to check whether certain things are chain maps, whether they the boundary is 0, and so on. Now, let's look at the compositions of F and G for a moment. If I take F1 and do it, I come up, and then I do G and I come back. And I have a little sphere in the middle. If I do F2 and come up and come back, then it's just the identity. So the best way for the situation would be that if I go up and back, it should be the identity on this one here, and that means that I should let F1 G1 compose to 0. So that's the first time we're going to make some extra assumption. Let's assume that F1 G1 composes to 0, and we can make that happen by having the value of a little sphere equal to 0. So we'll assume that a little sphere is equal to 0. Then you can check other things work. For example, if I do F1 and then I do boundary 2, I get this, right? F1 adds a circle, and then I do boundary 2, which is up here, and it causes a little cobordism over in here, and there's a little finger sticking up, but that's homeomorphic to this all by itself. And that's boundary 1 of F2, if you check it out, F2 and boundary 1. So this little topological finger works just fine and makes it into a chain map. So I'm just showing you little parts of it, but most of it actually. So all of this is working fine and giving us what we need, but we haven't yet worried about the homotopy. It's the other composition that is needed. I have to compose down and back up and ask whether that one could be chain homotopic to the identity. So we'll look, we'll do the exercise. So if you do that, then the essence of it is F1 composed with G1 plus the identity should be equal to the boundary of H1 and H2 boundary 2. And if you look at what that actually says, it says this. Here's F1 and G1, the one that caused a death and then a birth. You have this bit of surface hooked together. And here's the identity. And then we want that to be H1, and H1, I know you don't see the slide, but you remember how H1 worked. H1 and H2 were letting a circle die or letting a circle be born. And I won't bother you with going back to the details of the diagram. That's what happens when you paste them together. And then you look at this thing as a whole. And of course, it's not true in general that there would be any sense in which this should be equal. But it has a pattern. And the pattern that it has is you see a tube connecting here. And if it weren't for that, you just have the vertical walls and the cup and the cap. Here you see a tube here, and if it weren't for that tube, you'd see a cup and a cap and the vertical walls. And here you see a tube here, and if it weren't for that, there you just have the vertical cap, the cap and the walls. And here you see a tube here, and if it weren't for that, you'd see a cap and the walls. So what you are seeing is 4 bits of surface which are connected by a tube, one at a time. First, this pair is connected by a tube, then this pair is connected by a tube, then this pair is connected by a tube, and that pair is connected by a tube. And so, I claim to have reconstructed, perhaps Dror's thought, but we have gotten to the rule in any case, that you can start with 4 bits of surface, and then you can connect them a pair at a time with tubes. In this case, the pattern is across the middle, top to bottom, equals 1 to 4 and 3 to 2. That's the way we had it. And if you look at this in the abstract, you see that it looks like this. This is the algebra pattern of the tube connection. 1 to 2, 3, if I have 1, 2, 3, 4 written cyclically, then I have 1 to 2, then 2 to 3, then 3 to 4, and then 1 to 4. And Dror calls that the 4-2 relation. And what we have sketched the proof of is that if you assume that the cobordisms in the canopoly satisfy the 4-2 relation and that the value of the sphere is 0, then you're going to get invariance under the second Rademacher move. And more work will get you will show you that you get invariance under the third Rademacher move, and you really are getting a theory. You're getting an invariant of knots and links. So by going up to this categorical topological level, you can see what you need in order to get an invariant. And now we want to return, I've got to watch my time a bit, huh? We want to return to the algebra. And so one thing you could, now there are some things you need to notice. One is this: suppose that I have the 4 spots on 2 surfaces. Then I can connect by a tube here or here, and that will be equal, if you watch my conventions, to connecting here or here. So if you look at it that way, you see that if you have 2 surfaces, then you get an identity that looks like this: 1/2, assuming you can divide by 2, of the upper surface with a tube on it, plus the lower surface with a tube on it will be equal to the identity tube. Upper surface with a tube on it's a little torus. And so you get what's called the tube relation. All right? So the tube relation is a consequence of the 4-tube relation. And the tube relation can be symbolically written by putting a dot there that represents the torus. And then we're going to make the following move. We're going to say, well, let's suppose that that dot actually represents a bit of algebra. And with that and no more, or almost no more, we will return to the algebra and see the algebra come back. But before I do that, I want to show you an exercise which is very amusing. Suppose that you assume that for the tube relation, then you can prove the 4-tube relation. Because you see, if you assume this breaks apart, and you put in the 4-tube relation, which I've written here, you want to prove this is equal to 0, and you break this apart, then the left and right ends will cancel out. There'll be a dot on the right, and there'll be a dot on the left, on here. They cancel, so it all just alternates and cancels. It looks like it's part of something, some kind of cocycle condition, part of something larger. I don't know that. But I want to go to the algebra. So I'm going to assume the 4-tube relation, the tube relation, which I hope I've convinced you is really the same as the 4-tube relation, which I hope I've convinced you is really the same as asking for chain homotopy invariance of the structure. So now we're going to let dot be an element of an algebra, and let's call it X. And then we're going to ask, well, what does this say algebraically? Well, you need a couple more bits of algebra articulation at this point. Here you have the module, and here you have the ground ring, which I've just called Z. And there should be a mapping from this cup. It corresponds to a mapping from the module to Z, and we'll call that the co-unit. And there should be a mapping from Z to the module, and we'll call that the unit, and treat it as a unit. The identity element in Z goes to the identity element in algebra. And then what does this say? This says that if you put in an alpha on the left, you get the identity, so you get alpha. On the right, you get alpha times x, epsilon of it, multiplied by 1. And on the right, you get epsilon of alpha, alpha's coming in the top, times x, co-unit x, unit and x. So that's what the tube relation says algebraically, and what algebras will work for this? Well, now I'm down to an exercise. Let alpha be x, and you get alpha of x squared times 1 plus epsilon of x times x should be x. So this tells you that you should take epsilon of x equal to 1, epsilon of x squared equal to 0. Now put in 1, and you get epsilon of x times 1 plus epsilon of 1 times x. So epsilon of 1 should be 0. So we're finding out a lot. Now what about x squared? You put in x squared and you get epsilon of x cubed times 1 plus epsilon of x squared times x. Epsilon of x squared is 0. Tells you that x squared should be a multiple of 1. So we're back to the algebra we had to begin with, except that x squared isn't necessarily equal to 0, and it doesn't have to be equal to 0, as we'll see. And then for the coproduct, you play the same game, you see. I will decompose the coproduct form, x goes to coproduct of x, into using the tube, expand it using the tube, and then look at what happens when I input various things. If I input an x or I input a 1. And I'll spare you the pain of reading this by not going through it in detail, but it works you will see if you look into this little machine that I've drawn here and put x in, that it will come out k times 1 tensor 1 because of x cubed happening, and x tensor x. And if you put in 1, you get 1 tensor x plus x tensor 1. And we're assuming that x squared is equal to k. So that's the algebra. Let me see if I wrote it. Yeah, okay. So this is the most general algebra that will come out of this situation. And it comes out automatically by just doing the exercise that I showed you. And this exercise tells you that this slightly more general algebra than the original one will give you homology theories that are invariants of knots. And the invariance is coming from the canonical considerations. So instead of having the algebra come out as a Deus ex machina, you can see how it's related to the requirements for invariance. The one where k is equal to 1 is one that was studied by Yu-Sun Lee, and gives you a simpler theory that is very interesting and has nice consequences. Now, at this point, I may be out of time, so I should check. Am I out of time?
Almost.
Almost.
We started later, so.
All right. So I'll just go through a couple more slides of survey or something. Lee's algebra. Lee's algebra looks like this. This is what I just wrote. But you can rewrite a basis for it, an observation due to drawer like this. Rewrite it 1 plus x and 1 minus x like that. And then it has a nice form. R squared is R, G squared is G, RG is 0, and the coproducts take you to tensors like that. And then you can use that to see what the cycles look like in Lee's theory. Look at this picture here labeled with reds and greens. And if you were to meld these two circles, you get red times green. But what is red times green? Red times green is 0. So if you play with this, you see that it's a cycle. It has 0 boundary in the theory. And you can figure out how to label pictures of states from a given knot in such a way that you get all the cycles in the Lie homology. So the Lie homology is simpler, and it's generated by, in fact, ciphered smoothing states, oriented smoothing states for different orientations of the link, and then labeled in this kind of way. And once you know about the Lie homology, then now I'll skip that slide. Once you know about the Lie homology, then one can define the invariant due to Rasmussen, which counts elements in the Lie homology in terms of their grading, and gets you very nice information about the least genus surfaces that bound the knot in 4 space. And so Rasmussen, by counting in the Lie homology, was able to prove Milner's conjecture about the least genus surface that bounds a torus knot in 4 space. And with the help of Dror's nice way of labeling the curves for the Lie homology, one can see this a little bit more directly than the original papers show. But that's the way Rasmussen's invariant works. And I'll skip any calculations there. So this talk has been a walk through Dror's approach to Khovanov homology and finding relevant Frobenius algebras via the 4-2 relations. But we've done it in a different orders so that you find the 4-2 relation naturally when you're looking for relations on surface cobordisms that would render the theory invariant. And of course, there are many questions to ask here. One of the reasons why I've rewritten things in this way is because I'm working with Heather Dye and Aaron Kastner on Khovanov homology for virtual knots, and we generalized Rasmussen invariant in that direction. And so we wanted to understand everything as best we could, and this is some of the help in doing that, to go back this way. There are other questions that I'm interested in. I just wanted to mention them. Turner, Everett, Lipschitz, and Sarkar show how to produce spectra whose homotopy is Khovanov homology and spaces whose homology is Khovanov homology. Work in progress with my graduate student and myself, we show how to use the well-known, long-standing Dold-Kahn construction in simplicial work to do a similar thing, but it's basically a similar thing to Turner and Everett. And John Bryden and I have been working on seeing if we could put this in the context of the homotopy theory of this, in the context of étale homotopy theory. But in any case, the homotopy question is a very interesting one. You see from what I did with my bits of combinatorics here that this chain homotopy is a kind of nice miniature homotopy theory for understanding how Khovanov homology works. And it is possible to take chain homotopy theories and boost them to homotopy theories. But when you do that, however you do it, you end up adding a lot of machinery. And it would be really nice if there was a way of understanding Khovanov homology in a homotopy context that would bring more intuition to what's going on with it. So I'll stop there.
Questions?
Yeah.
You briefly mentioned these categorical grade actions where our matrices and cups and caps get functors associated to them.
Say it again.
Near the beginning of the talk, you mentioned this Morse diagram of
Yeah, Morse, right.
and constructions that assign functors to every crossing and to the cups
Right.
and caps. Could you say again whether there's a clear understood relation between that and the hypercubes and the state sums that you presented?
Well, that's the question I'm raising. I'm saying, on the one hand, you could think that we've done that too, right? In the sense that we have for each crossing a categorical arrow, and then we build a category and we're building a functorial situation. But we aren't doing the same thing that, say, Ben is doing.
Right.
We're not, Ben is producing a certain functor from a category to another category for each piece.
Right.
And then the whole thing becomes a functor from a category to a category. And then there's no cohomology yet. You have to do some kind of derived functors yoga in order to get a cohomology out of what he does or what other people do when they do that.
Yes.
So it fits into representation theory context nicely. I don't understand how to, say, take Ben's story, but that's because I haven't really read his paper, among other things. I mean, carefully, or understood exactly how those things work. But one should be able to see that if you keep following along their line, they will eventually land on the Khovanov complex if it's the Khovanov homology. And surely one does, but it's just kind of a long story, right? And the Khovanov homology manages to leap to an answer in a short story, and maybe it's just an accident of nice smoothings that it does, or maybe in general there would be a shorter story.
Thanks.
I don't know.
More questions? Let's thank the speaker again.